Hi geometry students, I hope you had a good weekend. Today's Monday and here is your lesson. This is the last new lesson for chapter 12, lesson 12.7, and it's about ratios and similar figures. So we're going to get started right away so that you can get your homework done right away and enjoy the rest of your Monday. Father in heaven, we just thank you so much for this day. I pray for my students that you would strengthen them and help them to do great on this lesson, to understand everything and to focus and learn well. And I pray, Father, for myself that you'd strengthen me and really help me to use the right words so that it's easy to understand. Thank you that you're faithful. In Jesus' name, amen. Okay, well, let's get started. So I'm going to sit down. We're going to get going here. I already drew the pictures to help expedite things. So go ahead and pause the video if you want to draw them. I'm going to get right into it. Okay, so we did a whole chapter on similar triangles, as you know, and here and there since then we've looked at surface area and different similarities, and this lesson really focuses on that completely. So what we want to look at is either prism shown below similar to one on the right? So here's the one on the right, and I want to look at both of these, okay? So how we know we have similar figures is that they have the same scale factor or the same side ratio. All right, and it has to work for all dimensions. So the first thing we're going to do is we're going to make a kind of a table here. So we're going to look at length, width, and height. All right, so we can't just look at one because they might have a similar length, but the height ratio is different or the width ratio is different. So it has to be all three consistent all the way through. All right, so I'm going to look here. I'm going to start with this figure on the right, and I see here that this is the length, and that is 4. And I'm going to compare it to the length of this one here, and that is 8. And that reduces to 1/2. So that ratio for the length is 1/2. Let's see if we have 1/2 for the width. Well, right here, this 2 is the width, and over here, this 4 is the width. So I'm going to have 2 over 4, and that reduces to 1/2. So far, these are the same. Okay, and then the height ratio, here's my height here, and my height here. I've got 2 over 2, okay? So that becomes 1 over 1. So 2 of them are the same, but the third one isn't. So the answer here is no. These two are not similar, okay? So if we named them A, B, and C, we would say that A and C are not similar, okay? Now let's look at the next one, which is B and C, comparing them, okay? So, going to go back to the length of 4 here, and the length in this one, in figure B, is 6. So we have 4 over 6, and that reduces to 2/3. Hey, can you guys keep it down in there? Yes. Sorry, voices kind of echo. All right, then here we have a whole house full of people tonight. The width is 2, and the width here is 3. So that's going to be 2/3. So far we're the same. And then the height here is going to be 2. And here is the height on this one, and that is 2/3. And you can see all three of these are the same. So we would say B and C are similar. So the answer to those two is yes. Okay? That's not well written. Let's try that again. All right, so you get the idea. If we have similar 3D figures, then all their dimensions will have the same ratio, the same scale factor, okay? Now, if we're not just looking at lengths and widths, single dimension, we might be looking at surface area or volume, which is a lot of what this chapter is about. So you want to pause the video here, I'll read it out loud, but this is our theorem. If two similar solids have a scale factor of A to B, two numbers that compare, then the corresponding areas will have a ratio of A squared to B squared. So area is two-dimensional, so it makes sense that the scale factor would be squared, okay? And the corresponding volumes have a ratio of A cubed to B cubed. And again, that makes sense because we have 3 dimensions for 3D, and that's volume. And so we're going to cube that ratio. All right, now we're going to use that. And here's number 2. You can go ahead and pause the video, and I'm just going to keep going. Cans shown below are similar with a scale factor of 87 to 100. Find the surface area and the volume of the larger can. So here's my larger can, and they give us the surface area of the small one, and they give us the volume of the small one. All right. So if we're looking at our scale factor, the surface area of 1 over the surface area of can number 2 is, for surface area, what do we do to it? Remember, I have 87 over 100. I square it, all right? So that would be 87 over 100, and they're both squared. And that works out to be 7569 over 10,000, okay? Sounds like a lot, but it all works out when we divide it out. Okay, so I'm going to set up a ratio because for my surface area here. So we're told that the surface area of the small one is 51.84. And I have my ratio here of surface area, can 1, over surface area, can 2. So I'm going to write that again, and I'm going to fill it in. So I'm going to put 5184 here. Now I don't know the surface area. These are blank here, now that I write them. See, this is what I'm trying to find. And I set that equal to my scale factor. Okay, but it's squared. Don't forget that. It's squared. It has to be for surface area. So now I can focus just on this, and I'm going to cross multiply and divide to get my surface area of the larger one. So I'm running out of room here. So I'm just going to do it. So let's see, I set it up like this. 51.84 times 10,000 is 518,400 equals my surface area of number 2. Well, I'm going to put it like this. 7569 surface area 2. And then I would divide by this, right? And you'll see it all gets back to a normal size.
My room's messy, just stay right there.
And I get the surface area is 68.49 inches squared. So that's the first one, okay? And that is inches squared because it's surface area. Okay, I ran out of room, so I'm going to go ahead and erase it. I hope that you got it all down. I didn't leave myself enough room. It's a good thing I can erase easily here. All right. Now, the volume of can 1 over the volume of can 2 is going to be a cubed over b cubed. So I'm going to cube 87 and I'm going to cube 100. All right? And when I do that, I will set up my ratio. So I've got 28.27, which is the volume I have here, over, I'm just going to use a V for number 2, equals 87 cubed over 100 cubed. So now I'm going to work those numbers out, and I get 2827 over V equals 658,503 over 1 million. Sure is good to have a calculator when you've got all those digits. All right. Now with this, I cross multiply, so I've got 658,503 V equals, and when I multiply that, I get 28.27 times 1 million, and I get 28,270,000. That's obvious, it seems. I just always like to check my work, make sure it's correct. And I divide, and it all works out, so I get a volume of 4293 inches cubed. Okay, so that's the answer. So I hope you see this is how we can use ratios, knowing that we square the surface area and cube the volume. We can use that to find whatever's missing that we need. Okay, now sometimes the question is, find the scale factor. So if I have two similar figures like this, I want to find the scale factor. So I know the volume, and that's my hint. The volume of P is at 1,000 inches cubed, and the volume of Q is 216. Okay? So if I'm comparing P to Q, all right, then it's going to be 1,000 to 216. Now that is the cubed version, right? Because I'm told it's the volume, so the numbers are already cubed. So if I want to find the scale factor, I have to do the opposite of cubing, which is to take the cube root of something, all right? So I'm starting with the numbers because I have the volume already cubed. So I want to take the cube root. So that's what I'm going to do. So on your calculator, you can figure it out, but basically you're asking yourself, what do I multiply by itself 3 times to get 1,000? So if you have your calculator, you take 1,000 and you push the cube root button, and 10 pops out. So we get 10, and then what multiplied by itself 3 times is 216. So I put 216 in, take the cube root, and I get 6. So I can reduce that, and it's 5 over 3. So the scale factor, or the length ratio, is 5/3. Okay? All right, we have a couple more. Number 4, I'll read it. You can pause this while you write it down. A store sells balls of yarn in 2 different sizes. The diameter of the larger ball is twice the diameter of the smaller ball. Okay? If the ball of yarn costs $7.50 and $1.50 respectively, which ball of yarn is a better buy? Okay? So let's look at this. I need the volume to know how much yarn is actually in each ball of yarn. So I'm looking at volume. I know the ratio of smaller to larger is twice. So A to B is going to be 2 to 1. The larger one is twice as big as the smaller. But I can't use that because yarn is a ball. It's the actual physical yarn inside of the ball. So it's the volume. Okay? So if I know I need to use the volume, I have to cube it, right? A cubed over B cubed. So I'm going to do that. 2 cubed over 1 cubed, which works out to be 8 to 1. Okay? So that is the ratio of the size of volume. The bigger ball of yarn has 8 times more yarn in it. All right? So this is the size ratio of our volumes. So you can write this down if this will help you. I need the volume ratio because I want to know the ratio of what is inside the ball of yarn. Okay, that is the 3D stuff. Okay, now let's talk about it. The ratio of the cost is going to be 750 over 150. And if I reduce that, that is 5 over 1. So these are the two things I have. I'm comparing 8 over 1 to 5 over 1. So if I'm going from smaller to larger, let's look at this. This one is, the larger one is 8 times bigger. We said that already. If I'm going by cost, the price increases 5 times. So actually, the volume increase is larger than the price increase. So the larger ball is a better buy. Size goes up more than price does, right? Does that make sense? I'm going to erase this over here. I know you probably get it, but I'm just going to repeat myself again just because it's good to hear it and maybe somebody else needs to hear it. So I've got 5 over 1 for price, and I've got 8 over 1 for size. So do you see, when I'm going from smaller to larger, the size increase is bigger. This goes up 8 times, the price goes up 5 times. So I'm getting way more volume as it increases than the price going up. So the larger ball of yarn will be a better buy, okay? So the larger ball is a better buy. Now, I just want to say something because this is going to come into play for your OYOs. If the ratios for the cost and the volume were the same, neither one would be a better buy. So if my price went up 5 to 1 and my volume went up 5 to 1, that means that both ratios increased 5 times. So the ratio doesn't change. You could reduce it down to the same thing, okay? So in general, if the ratios were the same for cost and volume, neither one is a better buy. Okay, that's important because of what you're going to do in your OIO. Okay, what I want you to do is try some right now. Tell whether the pair of right solids is similar. Okay, so you're gonna, this is just like number one, you're gonna do those. And so go ahead and pause the video right now and copy down these pictures, and then I left lots of space for us to do the work, and then I'm gonna show you the other OIOs. So pause it right now, and then we'll do some more copying in just a moment. Okay, now I want you to copy this one down. Cube C has a surface area of 54 units. Cube D has a surface area of 150 units. And you need to find the scale factor, find the edge length of C, and the volume of D. Okay, so go ahead and pause that. The dog, somebody just arrived. There's Johnny walking in the door. Go ahead and pause that so you can write it down. And then here's the last one. If a new price of the larger ball in number 4, so that's a ball of yarn, find the new price of the ball so that neither ball would be a better buy. So that's when the ratios were the same. That's your hint. Okay? All right. So go ahead and do those, and we'll come back in just a moment. Okay, we're back. So let's compare everything. Here's my length, 12 to 9. So I've got 12 over 9. That reduces to 4/3. This is length. Okay? This one is width, 16 to 12. Don't you love the easier ones now that we've done some of the harder ones? And then the last one is the height, which is 4 to 3. They're all the same. So yes, they are similar. Okay. Let's do number 2. So we're going to compare our 2 dimensions that are given for the cones. We've got 15 to 10 for the height, which reduces to 3 over 2. And then here we have 10 to 5. And that reduces to 2 over 1. So no, these are not similar. The corresponding sides don't have the same ratio. Okay, so that's 1 and 2. Let's go ahead and do number 3. Cube C has 54, all right, and D has a surface area of 150. Find the scale factor. Okay, so if we're working with surface area, we know that we have A squared over B squared. Its surface area is the squared function, and I want to find the scale factor is A over B. All right, so I'm told this is 54 over 150. Now this is going to get into a little algebra, so just if you got stuck, don't worry, we'll figure it out. So what do? We take the square root. So I have the square root of 54 over the square root of 150. Well, can I reduce that? Do you remember how we do that? What you do is you find the largest perfect square and you factor it out. Okay, so what perfect squares are factors of 54? Well, what are the perfect squares? We've got 4, 9, 16, 25, 36, 49, all of those. I hope you remember those from Algebra 1. If you don't, this is a nice little refresher, okay? So 54, let's see, does 4 go into 54? It does. Let's see if there's something bigger. How about 9? 9 goes into 54 6 times. Okay, how about 16? 16 goes into 48, so no, that doesn't go in. How about 25? Nope, 25 doesn't. 36? No, 36 times 2 is 72. Okay, so our largest perfect square that's a factor of 54 is 9. So I'm going to change this to the square root of 9 over the square root of 6. All right, so now let's think of 150. Let's start that process again. I'm going to list these and then I'll erase them in just a minute. My perfect squares are 4, 9, 16, 25, 36, 49, next is 64. Okay, that should be enough. Does 4 go into 54? 150. No, it goes into 144, so it doesn't. How about 9? Does 9 go into 150? Well, let me see. I'll use a calculator. Does 9 go in? Nope. How about 16? Does 16 go in? No. How about 25? I think that does. Yep, 25 goes in, so one of them works there. How about 36? Yes. How about 49? There's the dogs. No. And how about 64? Nope. And what's after that? 81? My goodness, I think the cavalry has arrived. Okay. 81 doesn't go in, and neither does 100. So the largest perfect square that goes into 150 is 25. Oh, and look at that. The square root of 9 is 3. The square root of 25 is 5. I have square root of 6's there. I can just cross those out. What's my scale factor? 3 over 5. So that's it. Now, remember, when it says the length of C, cube C, that is the scale factor. So length is the scale factor. So the, let's see, the length of C is 3, because it was C over D, so that's 3 right here. And then what is the volume of D? Well, D was 3 over, it was the 5 represented here. I'm going to erase this now so we can see it a little better, okay? This is, sorry it's kind of messy, cube C over cube D, right? So 3 represents the scale factor of C, 5 represents the scale factor of D. Well, for volume, we have to go back. So we use this and we cube it, and the volume of D would be 125. Okay? All right, we have one more. Okay. If a new price of the larger ball in number 4 above, that's a find. That's why this doesn't seem right. Find. Sorry about that. Find a new price of the larger ball in number 4 above so that neither ball would be a better buy. And we mentioned this up above. If the factors are the same, then they increase the same. So we had 5 over 1 and we had 8 over 1. Do you remember that? And these they're not the same. So find a new price of the larger ball. So the prices, do you remember, we had 750 over 150. And I want to find a new price so that, sorry, Thursday afternoon, I'm doing this too late. I want a new price for that. So let's talk about it again. I want to have the same scale factor of 8 to 1. So I want them to be the same. So the volume increases by 8 times. I want the price to increase by 8 times. Do you see that? So I'm gonna put 150 here and X up there. Okay? So the ratios will be the same. I cross multiply and I get $12. So if the ratios were the same, the larger ball of yarn would be $12. So it would go up that much. So it would look like this. Okay, but as we know, when you're pricing things, if you increase the volume, you're selling more. And very often, when the price goes up, or when the volume goes up, the price per unit will go down. Okay, that's it. I hope that you understand. If you have any questions, we can work that out, have some tutoring, anything that will help you. And I hope you have a good Monday. Bye now.